Hi and good morning everyone. The title of our project is Design, Analysis and Simulation of an AC Network using Thevenin Equivalent Technique. This project was carried out for the Electrical Principle 2 course. The study focuses on applying Thevenin's theorem to simplify a complex AC circuit, specifically a bridge TRC network, and then validating the theoretical analysis using simulation software. Through this project, we investigate how circuit simplification can make the analysis of voltage, current, power, and load behavior more efficient and practical in engineering applications. This slide shows the names and metric numbers of all members involved in this project. Each member contributed to different aspects of the work, including theoretical analysis, calculations, circuit modeling, simulation, data comparison, and report preparation. The project required collaboration to ensure that both the mathematical analysis and the simulation results were accurate and properly validated. Thevenin's theorem is one of the most important network theorems in electrical engineering. It states that any linear electrical network can be simplified into a single equivalent voltage source, called the Thevenin voltage or VTH, in series with an equivalent internal impedance called ZTH. In this project, we apply the theorem to a multi-component bridge TRC network. Normally, analyzing a circuit with multiple resistors and capacitors can become complicated, especially when the load changes. By replacing the original circuit with its Thevenin equivalent, the circuit becomes much easier to analyze, while still maintaining the same electrical behavior from the load's perspective. The objectives of this project are to determine the values of VTH and ZTH at an operating frequency of 1 kHz. Validate the theoretical calculations using multism simulation and investigate how changing the load resistance affects important electrical parameters such as load voltage, load current, active power, and power factor. The circuit selected for this project is a bridge TRC network. This type of circuit is widely used in communication and signal processing systems because of its ability to selectively respond to certain frequencies and create phase-shifting effects. From an engineering perspective, this network is important because practical systems often need to drive loads with different impedance values. Engineers therefore require efficient methods to predict how the circuit behaves under different operating conditions. By applying Thevenin's theorem to this circuit, the complex network can be represented by a much simpler equivalent circuit, making load optimization and performance analysis significantly easier. The first step of the theoretical analysis is determining the Thevenin voltage, which is VTH. This value represents the open circuit voltage measured across the output terminals of the network. After carrying out the calculations, the Thevenin voltage was found to be 4.23 volts RMS with a phase angle of negative 32.14 degrees. Next, the Thevenin impedance, which is ZTH, was calculated by combining the resistive and reactive components of the network. The resulting value is 1716.96 minus J450.45 ohms. The negative imaginary term indicates the presence of capacitive reactance within the circuit. These two parameters, VTH and ZTH, completely describe the behavior of the original network and allow for the load analysis to be performed using a much simpler equivalent circuit. The first load condition uses a load resistance of 220 ohms. Since the load resistance is relatively low, it behaves as a heavy load and draws a larger amount of current from the source. The calculated load current is 2.13 milliamperes, while the load voltage is only 0.469 volts RMS. The active power delivered to the load is 0.998 milliwatts with a power factor of 1.0. The low output voltage occurs because a large portion of the source voltage is dropped across the internal impedance of the Thevenin equivalent circuit. This demonstrates that heavy loads tend to draw higher currents but receive lower terminal voltage due to increased internal voltage losses. The second load condition uses a load resistance of 2 kilo ohms. Compared with the previous case, this represents a lighter load because its resistance is much higher. The load current decreases to 1.13 milliamperes, while the load voltage increases significantly to 2.26 volts RMS. The active power becomes 2.554 milliwatts, and the power factor remains 1.0. The higher output voltage is achieved because less current flows through the circuit, causing a smaller voltage drop across the internal impedance. As a result, a larger portion of the source voltage appears across the load terminals.
To validate the theoretical analysis, both the original bridge TRC network and the Thevenin equivalent circuit were developed using multisim life. Two operating conditions were simulated, namely RL equal to 220 ohms and RL equal to 2 kilo ohms. The purpose of performing both simulations was to verify whether the simplified Thevenin circuit could reproduce the same behavior as the original network under different loading conditions. One limitation encountered during the simulation was that Multisim Life did not provide a dedicated component for directly representing complex impedance. To overcome this issue, the capacitive reactance of negative J 450.45 ohms was represented using a capacitor with a value of 353.33 nanofarads at the operating frequency of 1 kHz. This approach allowed the simulation model to closely approximate the theoretical impedance while staying within the software's component limitations. For the first simulation condition with RL equal to 220 ohms, the measured load voltage is 0.4764 volts and the load current is 2.1600 milliamperes. The active power delivered to the load is 0.998 milliwatts and the phase angle is negative 19.048 degrees. These results closely match the theoretical calculations and confirm that the simplified Thevenin model accurately represents the behavior of the original circuit under heavy load conditions. For the second simulation condition with RL equal to 2 kilo ohms, the measured load voltage increased to 2.3076 volts and the load current decreased to 1.1538 milliamperes. The calculated power is 2.531 milliwatts and the phase angle is negative 25.232 degrees. These values again show excellent agreement with the theoretical predictions and clearly demonstrate how increasing load resistance significantly change the voltage and current distribution within the circuit. The comparison between theoretical calculations and simulation results show that all percentage error remain below 2.2%. For the 220 ohm load condition, the voltage error is 1.58% and the current error is 1.41%. For the 2 kilo ohm load condition, both the voltage and current errors are approximately 2.11%. These differences are extremely small and indicate that the mathematical model is highly accurate. The minor discrepancies mainly originate from software limitations, specifically the 5-component limit in multisim. To satisfy the limitation, certain components had to be combined, which slightly altered the current paths and produced small deviations from the theoretical values. In conclusion, this project successfully validated the application of Thevenin's theorem in simplifying a complex bridge TRC network into an equivalent circuit consisting of a single voltage source and an internal impedance. The analysis demonstrates that load resistance has a significant effect on circuit performance. A heavy load of 220 ohms produced a high current but resulted in a large internal voltage drop and low terminal voltage. In contrast, a lighter load of 2 kilo ohms reduced the circuit current and significantly increased the output voltage. Finally, the close agreement between the theoretical calculation and the multisim simulations with error remaining below 2.2% prove that the Thevenin modeling is a reliable and highly effective engineering method for analyzing complex alternating current networks. So that's all from me. Thank you for your attention. This concludes the presentation on the design, analysis, and simulation of an AC network using the Thevenin equivalent technique.